Sounded fancy. Okay, so we're going to do a series of increasingly difficult problems. I want to give a note and a call out, and I'm sorry if you're watching this from Zoom. Sorry, not sorry, kind of, I warn you. That what I'm going to do today is really teaching by example. There are a lot of techniques and things that I'm a point to that are not necessarily written exactly, literally verbatim on the slide. I want you to learn by seeing, learn by doing, rather than just reading it. So if you're not here, I'm preaching to the choir here, if you're not here, this gets a lot harder to learn from. I'm going to walk you through how to do these rather than have something you could just read. If you want to just read, by the way, there's also the textbooks. Anyway, so that little caveat warning having been put in there, let's dive in and start doing. You will see that the Newton's laws and the stuff that we've started can be applied to a billion different scenarios, conservative estimate. And this, frankly, is probably my favorite part of the semester, seeing how diverse you can apply force dynamics methods to. Okay, so as I said before, when I say dynamics, I want you to think force, I want you to think push and pull, I want you to think Newton's laws. And our first level look at forces, what's a force is, it's a push, it's a pull. The harder the push, the harder the pull, the bigger the force. And I want to emphasize that pushing something down versus pushing something up has a different effect, right? Force is a vector quantity. For our purposes, for now, we're going to be talking about one dimension, left versus right, down and up. And we indicate the direction in one dimension with a plus or a minus sign. Positive forces are going to be upward forces, rightward forces. Negative forces are going to be downward forces, leftward forces. Push versus pull does not matter. If I push something to the right, if I pull something to the right, that does not matter. What matters is that the force is to the right. Which direction is it getting moved? Which direction does that force try to move it? Does not necessarily get moved in the same direction that a force acts on it. Unit for force is the Newton. 1 Newton is, if you apply 1 Newton of unbalanced, also called resultant, also called net force, 1 balance of net force will accelerate a kilogram worth of matter at 1 meter per second squared. If you apply more force, you get more acceleration. If you have the same force and more mass, you get less acceleration. That's Newton's second law. We'll get there. Doink, doink. Okay, now here I haven't yet told you this, so listen up carefully. Here are probably the 5 most important forces that we're going to deal with. I might throw in something here and there, other kinds of forces, but here is sort of your zoo of the most common forces, not animals, zoo of the common forces that you need to know about. Each of these is going to have an idea, an equation, a model, a description, things to know about it. We will build up from simple to complex over time. I'll introduce the facts of each a little bit at a time. Weight, we've already talked about. What's the equation for weight? Weight force equals negative mg. Remember, there's a difference between m and w. What's m tell you? Mass. And what does mass mean? What's its essence? How much stuff? Good. What's weight tell you? How hard a planet or a star or whatever pulls on that stuff. And what's g? G, what I call that is gravitational field. G tells you how hard, how many newtons each kilogram gets pulled by that. In free fall, acceleration is also negative g, but I don't think that's the essence of g. I think the essence of g is the strength of the pull on each kilogram of mass. Anyway, so you know a lot about weight already, and we're going to practice still more. Weight, please note, is the only long-range force. Every other force, this is very important, every other force that we deal with in this entire class, if I'm not mistaken, I can't think of an exception, is a touch force. If it's not touching, it's not forcing. Very important. One of the biggest screw-ups you could possibly make when you're starting to do complicated force problems is to miss a force, not to be able to identify what is causing a force, not to be able to identify the kinds of force. And it is quite simple if you remember, if you think about this, if it touches, it might force. It doesn't guarantee, a touch doesn't guarantee that there's a force, but for there to be a force, it must touch. Go through the list of everything in contact with the object, those can exert force. Weight is the only exception to that. Normal, friction, tension, spring are all touch forces. Let's talk about these briefly, one at a time. Normal force is only when you have two solid objects touching each other. And in particular, the word normal does not mean everyday, common, or usual. I mean, it is a very common force, but that's not what normal means. Normal means right angles. So normal force is perpendicular to a surface. If here's my hand, and I'm pushing against my hand is exerting a force this way. This way. It is at right angles to my hand. Friction is the parallel bit of contact. That is to say, friction is when two solids rub against each other or try to rub against each other and don't want to. Friction is a solid-solid interaction. It is always parallel to the interface. If I have this hand rubbing against this hand, friction is moving left and right. When I'm moving my hand right, it is exerting left. When I'm moving my hand left, friction is exerting right in that case. It is not up and down. Friction, no pointy uppy down. Friction points back and forth along. I call it as a resistive force when two surfaces are in contact, and they don't have to slide over each other, but they have to be trying to slide over each other. We'll talk much more about friction later. We did a lab last week with a lot of friction in it. We'll talk more about that. Tension and spring are very intimately related. Both are, you're connected to a rope, a string, a chain, a spring, a coil of wire or something. The big difference is tension is if we don't care about how that thing elongates, gets longer as you pull on it, and spring force is if we do care about how it gets longer. For instance, suppose I've got a string dangling and I pull on it. Is it getting longer? Well, yes, actually, if you look really closely. If you measure with a micrometer or whatever, you'll see even medium strength pull on an ordinary string, it does stretch a little bit. What happens if I take a slinky dangling it from the ceiling and pull on it? Well, then there's a big stretch, right? So if I care about the stretch, if it is relevant to my problem solving, in the string case, do I care about those micrometers? Maybe, maybe not. I would model it as a spring. If I don't care about the fact that it's getting longer, I'll just call it a tension and be done with it. When do you use which? It depends on the problem. You have to think about it. These five forces are not, if you see this, then you do that. You have to think about the situation. These are not fundamental forces that are always applicable. They are models that we apply to represent some particular situation. Ultimately, the only fundamental here is weight force. Weight force can't be broken down. Every one of the other forces in here, every other force we will talk about can be broken down ultimately into electricity, but we're not going to go there. There are other kinds of force. If I give you a problem involving them, I'll just tell you a force acts. Some force of this magnitude in this direction acts. I don't have to tell you the kind of force. If I tell you the kind of force, there are additional ideas that you need to connect with that. If I don't tell you the kind of force, then those details are irrelevant. Capiche? Thank you, Sensi. Okay. Here are Newton's laws in short. If an object is not accelerating, forces must be balanced. If an object has balanced forces, then the object cannot accelerate. If something is accelerating, then there must be a net or an unbalanced, a total force acting on it. You could find the magnitude of the acceleration by dividing total force by mass. And I do want to emphasize these are both vectors. You could find which direction the object is accelerating by the direction of net force. Mass doesn't go negative. Third law, if A pushes B, B pushes A. And this is harder than it looks. And the exam questions involving the third law showed that it's harder than it looks. We're going to be spending a significant amount of time. We're going to start talking about some problems that involve this today. We will have an entire class later that focuses just on solving third law problems, recognizing third law scenarios. I do want to, or I should probably also point out, if A pushes B, B pushes A in the opposite direction and equal strength. Not just that they exert a backwards force, a reaction force, a third law pair force, but they're the same strength kind, opposite direction force. So far, so good. All of this, except for the list of forces, should be review. Google form, go to the Google form. Question A, tell me where you're confused. Tell me a sticky point, tell me something I went too fast over. Tell me something you want elaboration on. Tell me where you're at. I get it, makes sense. Nothing, nowhere, not confused. Good, I'm good. Tension and spring. Friction. Okay. Tension and spring, tension and spring. Difference between friction and normal, okay. Okay, so the big thing I'm seeing is tension versus spring. Tension versus spring, these are two ways we can analyze the same scenario, and which one you use depends on what you care about. If I've got something dangling from a slinky and I'm pulling it and it's getting longer and shorter and I care about where the object is, how hard it's pulled on the slinky, whatever, then I would use a spring model. I'll teach you equations for what that means, how to analyze that. But if the object is just dangling from the spring, not going up and down, and I don't care about motion, I might use the string, the tension model, and say, who cares that the thing pulling it upward could stretch? I'm just going to find the tension in the spring. You don't have to use the spring equation that we'll talk about eventually. Not today. However, you can. You could apply that, and that will still give you a correct answer. So which one you apply depends on what you're asked about. It's not unlike, look, we did position, velocity, acceleration, time, initial and final velocity. There's more than one way to solve a given problem, right? And there's more than one variable that you could solve for, right? We've done a billion problems like this. Well, what I'm saying is tension and spring models are kind of like, which equation do you use? Well, what do you want to find? Apply the relevant equation, analogous to that. And the other big question I saw was normal and friction. First off, let me emphasize, we're going to do a lot more about this as time goes by. But normal, briefly, is what's keeping this water bottle from phasing. By the way, whose water bottle is this? Anyone in here? Someone left it in office hours? Okay, maybe from the 4:30. Normal is what's keeping this water bottle from phasing through the desk. God damn it. And friction is what slowed it down. Friction was acting left-right to slow down its rightward motion. and normal is acting vertically and kept it from falling through the table, opposing gravity in this case. It's not always true that those are the directions, by the way. That worked because this table was vertical, horizontal. If the table is vertical and you press it against, well, different things can happen. We'll get to that eventually. So that suffice for a first look at friction and normal to distinguish between them. Okay. Why does the slide say solid, solid, and not solid? Hey, here's a good one. Again, why does the slide in the previous picture say solid, solid? Because every force is an interaction between how many objects? Two. If one of them is solid and one of them is gas, then we're talking about a drag force or a lift force or something. If we've got a liquid on a gas, oh God, I have no clue how to model that. I've never done that personally. If we've got a solid on a solid, that's one kind of force, one set of force models. If we've got a liquid involved for one or both of those, we'd use a different set. I'll tell you that liquids and gases, those force models are god-awful complex beyond the scope of the course. We're not going there. You may care about that if you're in advanced chemistry classes, but no, for here. Okay, touch force, yeah. I will frequently refer, by the way, touch force, push force. I apply a force. I want to emphasize again, if I don't tell you the kind of force, then it doesn't matter. I'm telling you that there's some force being exerted on the object, and I'm going to tell you enough to analyze the scenario, but the kind of that one doesn't matter. As it so happens, if I push on something, I'm exerting a force, I'm solid. I'm exerting a force at right angles to the surface that I touch it at, that's a normal force. But I will very often skip saying I exert a normal force on the object. I'll just say I push the object. Okay, write this down. Think about each one of these. This should make some kind of common sense, but it's harder than it looks. And I'm going to point you back to this list again and again when we're doing analysis. 1, here's how to find forces acting on an object. 1, is there a star or planet nearby? If so, include weight. I should say, if you care about the vertical direction, star or planet, include weight. If I have me walking horizontally along the ground, running from place to place, there's a weight force on me, but that's not what's speeding me up, slowing me down. Vertical forces are irrelevant in this sideways motion as I'm pacing back and forth. So I should say, if I care about vertical direction, a weight force applies. 2, make a sketch. Your sketch does not have to be artistic. Thank God, mine certainly aren't. What I'm going to encourage you to do is actually, you're going to make a sketch of the scenario, draw a bubble around the object in question. Think about this. Then make a second sketch. I'll demonstrate this myself. Second sketch where you simplify the hell out of the scenario and only draw little arrows to show strong, weak forces. Okay, but when you have a first sketch, when you're visualizing the scenario, a person is skating across an icy lake, you'll draw a little pig person, you'll draw a surface underneath them to represent the lake, draw a little dotted bubble around the object. Anything that crosses the dotted line may, doesn't have to, but may exert a force. When you consider the objects that can exert a force, then you can identify what kind of force based on the dictionary I just gave you. It'll be one of those 5. And if you've already included weight, it'll be one of the 4. I say may exert a force. Let me give an example of when there's a force that could exert but isn't. This water bottle sitting on this table right now. It's in contact with another solid object that is capable of exerting friction. You saw earlier that it can exert friction. Is there anything pushing this along right now? Is there anything pushing on this horizontally? No. Is there anything at all that would exert another horizontal force? Now, the only thing that can exert a horizontal force, the only thing besides in the horizontal direction that can exert a force is the tabletop, friction force of the tabletop. If there's nothing pushing it along, this is a not moving water bottle, its acceleration is 0, there must be no net force. So I can conclude from looking at this, the table could friction on this, but it's not. If there were a friction force acting on this water bottle, it would start to accelerate. Okay, let me give an example of when I can have friction acting. Let's look at this small bag on top of this big bag. I'm going to make the big bag exert a friction force on the small bag. I'm going to make this act on this by moving them. I moved the lower bag and the upper bag came along for a ride. What force acted on the upper bag to move it along? Google form B. What force acted on the upper bag to move it along when I pulled it across? I'll give you a hint. It's not my hand. My hand no touchy the top bag. My hand no exerty a force. What kind of force was exerted on the top bag? Don't tell me the thing, tell me the kind for this. Again, take a look up here. If you do not know what I said, take a look up here. I've got a bag sitting on a bigger bag. I'm going to make this big bag exert a force on the upper bag. Lower bag, pull the upper bag along. What manner of force pulled this upper bag along? What kind of force was there that pulled the upper bag along? I will give you a hint. It is not my hand based on what you just heard. Based on what you just heard, if it doesn't touch, it doesn't force. This is not a gravitational force. My hand does not gravitate it. I am not that heavy. So it is not a hand push force. All right, and the answer is about 3-1. The correct answer. Let's talk about why wrong answers are wrong. Which direction does the normal force point? The surface is horizontal. At right angles to horizontal is vertical. In this case, the normal force of this bag on the upper bag is up. Which direction is wave force point? Last I checked, gravity pulls things down. Are these up and down forces capable of pushing something left to right? No. If you said weight or normal, think again. Weight and normal act up down. Here, I can make the weight and normal move the upper bag, but if I'm moving it horizontally, vertical forces can't do that. What other kind of force could have been involved? Correct answer is friction. Friction is the force that moved that upper bag. I moved the lower bag beneath it. The lower bag pulled on the upper bag horizontally with a friction force. If you drew a dotted line, at least in your imagination, around that upper bag, do you agree that the only thing touching him is the lower bag? All right. So then you think, is it normal? No, vertical. The only other possibility is friction. Okay. Now let's do exercises, examples, whatever. I have had some people complain about me giving questions that you do not know yet how to do the answers to. I do not do this to be mean. I do not do this to be a jackass. I mean, I am mean and jackass, but that's not why I do it. There's educational psychology that says that when students are simply shown how to do a problem, the learning is about this much. And if they try, if they engage, if they do anything at all besides watch an instructor, if they engage with the problem and start to think about it, even if they get the answer wrong, they learn this much by doing it. So I give you the problem and ask you to think about the scenario because there's a real measurable proven learning difference in how much you take away from it. That said, let me encourage you at the very least here, to sketch the scenario, draw a bubble, and think about the forces acting, and then apply Newton's laws, if applicable. This will be Google question C. Start this off. And I'll tell you how I see it. See how I think about it in a second. Turn to your neighbor. Talk to your neighbor, though. It's good for you. Also proven. You don't need to know a darn thing about tension, by the way, other than that it's what ropes exert. Let me give feedback, steer you away. There are a couple of wrongo answers that I want to steer people away from. How do we measure forces? Tension's a force. How do we measure forces? What are the units? Do we measure force in kilos? No. If you told me kilograms, you're thinking of mass. The answer is not 55 kilograms. Okay, let's bring it together. Let's practice the skills that we just did. This one, many of you got right. Great. If you got it right, don't be complacent. I still want you to go through the darn process, the step-by-step process. Trust me, this gets much harder. So do the process. And we're going to build up from simple to complex. If you got this wrong, chillax, you're fine. Here's a roof. Here's a rope. Here's a gymnast hanging from their apparent head. Okay, whatever. I don't know how gymnasts go. Do I look like someone who climbs ropes a lot? Whatever. All right. So, do you agree that this is a reasonable sketch? Forget the head, but that this represents all the objects that are interacting with the gymnast? I draw a dotted line around. What possible forces could there be? Are they near a planet? Every gymnast I've ever seen on TV has been near the Earth, so yes. So what do we include if there's a planet nearby? Wait. Wait for what? Yes, a weight force. Is there anything passing through this bubble? There's nothing there's no line going through this bubble? Yes. Yes, it's right here. There's a line passing through this bubble. Now, what is passing through the bubble? Is it a semi-truck? Is it a... It's a rope. What do we know about ropes? We could use a tension or a spring model. You haven't learned about springs yet, so a good guess is that you should apply a tension force. Now, I'm going to strongly suggest, follow along with this. This problem, you don't have to do it this way, but I want you to practice the skills that go into it. Here is the second version. This is called a free body diagram. Here's the second version of the person. And I'm going to draw two arrows that represent the forces acting on the object. The tension force points up, the weight force points down. Now, there's an equation for weight force. I will never tell you the equation for tension force because there isn't one. You deduce the magnitude of tension and direction based on other things in the problem. So there's an equation for this, but not that. Yet I'm telling you that you can calculate that. Let's consider Newton's laws here. What laws might apply to calculate, to analyze this scenario? What's happening with their motion? What does it say in the problem about their motion? They're motionless. What's their acceleration if they're motionless? 0. What do you know about total force? Total force must be 0. I claim that if I'm writing down the total force equation, there's the total force. I write up the individual forces acting. There's an upward tension. I include a positive sign. There's a downward weight force. I include a minus sign. I am adding up all of the possible forces. I claim Newton's first law, it's at rest and staying at rest. Actually, it doesn't need to be. It's simply not accelerating. Net force must be 0. No unbalanced forces. So actually, these two forces have the same magnitude. Sometimes I put little tick marks like that to indicate that those are equal magnitude. If you did geometry, this is a common technique. Hey, how do I calculate the weight force again? mg, right? I could do that. I could plug in. Oh, for God's sake. I could do that. I could plug in. If I plug in m times g, I get that the weight force is 540 odd newtons. And if 540 is mg, I can simplify this equation, and I get tension is also 540 newtons. So far, so good. This isn't every problem we're going to do, but these are some of the problems we're going to do. Let's review again the steps that we did. Sketch it, think about the identity of forces. Write down the identity of those forces with little arrows, labeled arrows, showing which way. Write down Newton's law. In this case, there is no acceleration, so the right hand is 0. Here are the forces that add up. I made sure to include direction, by the way. Direction on downward or leftward or whatever forces. And then I can apply a model. The model of weight force is mg, negative mg. Plug in, solve, bang. Tension force in the rope is 540 newtons. Yeah. Net force has to be 0, otherwise there would have to be an acceleration. Good question. Other questions? Okay, now let's make it ever so slightly harder. Here we go. Read carefully. Put this in D, by the way. Tell me D. Answer. Makes me happy. There are so many correct answers. Sorry, this is so intimately related to the last one. I'm going to say only 2 minutes left to analyze the sucker. I'm going to emphasize here, I'm asking for tension. That's a force. If you tell me a velocity or an acceleration, that's not what I'm asking for. Find the tension. That's a kind of force. Also, you cannot add 1 to 540. I mean, you can, but you're adding different kinds of things there. And I'm going to call that, if you're there, time's up. 54 people. 55, actually. All right, I'll take it at this stage. What's the difference between this problem and that problem? What's the acceleration in this problem? 0. 0 acceleration. So what's the difference in the force in this problem and that problem? Nada. Nichts. Zilch. 0. Nothing. No difference whatsoever. Newton's first law tells us that it doesn't take an unbalanced force if you are moving steadily. Conversely, if you are moving steadily, if you are not accelerating, if your velocity is not changing, then there can't be a net force. The force analysis is exactly the same as before, 540 newtons. 539 rounded to 2 sig figs. Okay. Questions, feedback, comments, ideas. Your hand is slightly vertical, you have to ask. Well, tell me about the previous problem. There are steps here. We're doing this a very step-by-step process. Do you feel comfortable with this? It's a new skill. It's okay if the answer is no. Okay. The biggest step here probably that I took without writing it down is recognizing that this is an example of Newton's first or second law. If we write it as the second law, that's an equation. Acceleration is 0, yeah? Staying 0, motionless and staying 0. finding the net force, actually, I should have made a bigger deal about this going through this, because when I was doing this last week with my lab sections, finding total force proved immensely difficult. So let's think about this. To find the total force on something, you add up the individuals. But you have to recognize T and W point in opposite directions, so W is a negative value. So are you okay with the total forces being T minus W? From there, how about W being mg? Negative mg. Yes, still good? Okay, if I plug in the numbers, mg is 540, rounding to 2 sig figs. Solve for tension, 540, yeah? Okay, now I want to go back through this exact same process. Tell me what's different if our velocity is 1 meter per second. Does that change a darn thing about the left-hand side? Does that change what mass is? Does that change what acceleration is? No, you see that? Okay, there you go. Everything else proceeds the same as before. Other questions? Ask. Ask while there are only a couple of pieces. We're only going to add more. But also, as we add more, you'll get experience with it. Some parts will seem easier, some parts will seem harder. Okay, I see no hands, so let's move on to exercise. What are we at now? Here's E. The forces are, well, good. Analyze, analyze. Question before, where did I get 540? 540 is what happens when you multiply 9.8 times 55, mg, and then you round to the correct number of sig figs. 2 sig figs in, 2 sig figs out. I'm not testing you on sig figs. I'm not focusing on that. So if you wrote 539, that's also perfectly acceptable. But you should recognize that 539 and 540 are about the same number. And I'm going to call times up, and we got 2/3 of the class wrongo, or absento. So let's build this up. Let me teach you Socratically. True or false? True or false? Here's question E. Think through this. Are there any new forces acting on the object? Question F. Are there any new forces acting on the object? Question F is, are there any new forces acting on the object? True or false? Yes or no, whatever. Okay, so let's follow this up. Weight is still there, right? And weight hasn't changed. The planet doesn't care if you're moving, accelerating, blah, 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 blah. Every other force is caused by something touching. Let me ask you this, what new object is touching the gymnast? I will also remind you that to be a thing which exerts a force, you must be lickable. What lickable object, question G, what lickable object is newly touching the gymnast? What new object is exerting an upward force on the gymnast? To be precise, I've got several people telling me there's no lickable force. Force is not lickable. I cannot lick tension, but I can lick a rope. A rope is an object capable of exerting a force. I can lick a table. The table can exert a force. What kind of force? A tension force, a normal force, whatever. I can't lick normal force, but I can lick an object which can exert the normal force. Okay, so again, the question is, what new object is exerting a new kind of force on the gymnast? What new object is touching the gymnast now? I'll give you a further hint. This was an object that is not touching beforehand. So the gymnast is sitting there, the gymnast is climbing steadily, now the gymnast is accelerating. What new object is exerting an upward force on the person, gymnast, that was not there before? You're still at a quarter of the class here. I want to emphasize this. Did I say a darn thing about a new thing touching? Is the rope new? There's no new object. There's no new force. Many people, about 15% of the class, said that the rope is a new thing touching the gymnast. The rope was touching the gymnast before. That's not new. The magnitude of tension is going to be different, but that's not to say there's another force acting, to say that one of the existing forces is changing. Okay. Also, about 5% of y'all told me that their hands are the new object. Oh my God, they didn't have hands before? Also, I will say that your hands are part of you. I would never analyze your hands as a separate object. Maybe unless you're Mickey Mouse or something like that, and have just gotten a bee sting and the hand swells up to be bigger. No. Okay, there is no new object. There is no new force. I think a number of people, I heard this out loud. I don't know how many people said it, but many people, at least a couple of people, said acceleration is a new force. Acceleration is the result of forces. Acceleration is not itself a force. Acceleration describes your motion, not a push, not a pull. The cause is the forces. The effect is the acceleration. Cause is not the same thing as the effect. Okay, so the correcto answer for what I've been guiding you up here is there are no new forces, and we can write down the same equation that we did before. Oh, I know the mass. There are no new forces. I don't know tension, but I do know that gravity doesn't depend on your motion at all. Gravity just depends on being near a planet. Bazinga. And then you plug a solve a solve. Zoom in on this.
These units cancel each other?
What?
The units,
Units of what?
the 55 kilograms and the.
1.3, not 31.
Yeah, yeah, math, right. So in math,
Kilograms times acceleration is newtons.
oh, that's what I'm. And then,
Okay, questions here. I want to emphasize something. I want to emphasize something big here. Once you do the sketch and turn that into a force diagram, the dot is the object, the arrows are the forces acting on them. Those arrows might change their length, their strength, their whatever. I guess it's conceivable that they would change their angle, although we're not going to do things at an angle for the most part. I can think about. That step is done. You've included all the things acting on the object. Unless there are new things that go in the sketch, there is nothing new that you can add to the forces. I guess if you didn't include friction, that's the only exception I could think about. If you didn't include friction and now there's a need for friction, that's the only new thing that could possibly be involved. Once you get the force diagram, the arrows up and down or left and right or whatever, that leads directly and exactly to writing down net force. Net force is just add together the forces and include minus signs for downs or lefts or souths or whatever. Once you write the total force, you can use the magic incantation F net equals mass times acceleration. Plug in, you're done. Every darn time. Another follow-up question. Previously, the rope was 550. Now the rope is 610. How does the rope know? How does it know to be bigger? I claim part of this answer is that if I pull on the rope harder, it pulls harder on me, Newton's third law. It doesn't need to know, oh, hey, not Tucker, oh, hey, the gymnast is accelerating upward at 1.3 meters per second squared. I better calculate my new tension force. that I need to exert on them. No, you don't need to do that. It doesn't need to think about that. It doesn't need to think at all. All it has to know, all that has to happen is when you exert on a force, when you exert a force on it, it needs not to break the laws of physics. It will pull upward on you with the same force you exerted on it. So what happens if you move your arms down and they're holding on to something, you're moving your hand against it. There's a bigger upward tension force that you're getting pulled on with as your arm contracts. The rope pulls harder on you when you pull harder on it. Turn to your neighbor and express that idea real fast. How does the thing know to exert a bigger force? Why? How do you know?
Oh, you like that? There's daggers. My soul goes out. I know exactly. That's why I'm staring at it. I said it. The wall. That often is the same by something.
So when I plugged into my five times 1.3 and 71.5 and even rounded up to 17, I got 612.
How many significant figures are there? 1.3, 55, 2. There are 2 significant figures. At the end of the day, you round to 2 digits.
So would I just do 71 then?
No, don't round intermediate. You get your final answer, 611.5. Then you round to which digit? Tens. If I round to the tens digit, that gives me 2 sig figs of precision. 611.5, 610. By the way I have set up the course and so on, sig figs are, I do not think the central point of this course. I've dropped them from doing. I will never give you a test where the 2 answers are just one is correct sig figs, one is not, and you have to get the right one. I'm not teaching the skill, so I say screw it. Sure. So always, if you get something slightly different than mine, very slightly different, one rounds to yours, you did it right. Okay, questions. I want to do one more before we get out of here. We only have 8 minutes. Questions before we move on about any of this? Let's do one more. Let's do 2 more. This one's a fast one. Talk to each other. Talk to each other and vote 1, 2, 3. This is question H. This, you don't have to numbers. This is, by the way, exact scenario I ask on midterm 2 and the final. Elevator speeding up, slowing down, moving up, moving down, tension, weight. Very common question.
I feel like it's the pulley system, right? Something like that. So should have less and then the way no. It slows down.
These are not third law pairs. Tension on elevator, cable on elevator, planet on elevator are 2 different A's and B's.
That was right. I was thinking. It is regular, right? Yeah, so the velocity is like gonna.
Okay, time's up. Time's up. Is the object accelerating? Yes. Which direction is the elevator accelerating? Down or up? Point. Point for me. Let's have a class vote. Point big. All the way up, all the way down, so I can see the whole class at a time. Ah, happy you think it's up, happy you think it's down. Tell me, what's the condition to slow down? What's true about velocity and acceleration if you're slowing? They're pointing opposite directions. If the velocity is downward, which is the acceleration? Moving down, negative velocities, which are getting closer to zero. Don't I have to add positive numbers to negative velocities to get them closer to zero? The acceleration is upward. Which force must be bigger then? The upward force or the downward force? If acceleration is upward, net force is, that's one of the big laws I said, the direction of the total had better match the direction of the acceleration. So which one wins? The one pointing up. The only force upward on the elevator is its tension force. Okay, again, here's how to reason through this. I got a third of you through this. The other third were either, 2/3 were either wrong or not there. So let's step through it one piece at a time. You have to learn the acceleration. You have to remember how to find accelerations. In this case, just the direction of the acceleration. If it's slowing down while moving down, that's an upward acceleration. Part 2 is to recognize what forces are acting. Well, we just did a whole bunch of problems just like this, so I hope that it's okay that there's a tension up and weight down. Step 3, recognize that the total force had better be positive if acceleration is positive. Okay, so if the total force is up, what's up? What's up? Tension. Nothing much, what's up with you? That's right, is the other correct answer. Okay, turn to your neighbor and discuss real fast. How do you walk through this? And what step are you getting lost on?
So I did, yeah, because I was guys that said, gotta be opposite. Yep, yep, so nothing going up, nothing's going up.
Okay, next class is nothing but examples. The homework, very important. The homework from last week that I pushed back till this week, I will add a couple of more problems to it. There are only 10 questions on it so far, and you're getting 2 weeks to work on it. That will be due on Sunday, 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 Sunday. It is posted. I'm adding questions to it. Do not forget to do the final set as it will be posted on Wednesday. Get out of here. I love you all.